Hi guys, welcome back to another session of Physics with Fazil. So this will be our last session dealing with refractive index. So in the last class we were learning something about the refractive index of materials. Refractive index is a number, is a measure, is a value which indicates the optical density of a transparent material. Optical density of a material then can be determined using or by knowing the refractive index of the material. If a material has higher refractive index, then the material is said to be of higher optical density. In this manner, we came to define two different types of refractive index, but the definition implies the same. Refractive index always has the same kind of definition, but in a manner in which we define it differs depending on which two materials we are using. If the material being used consists of vacuum in it, the free space, the vacuum, then such refractive indexes are referred to as the absolute refractive index. As you can see here, refractive index defined in its absolute terms, or whenever you refer to a material's refractive index, implies its absolute refractive index. And how do you define that? The absolute refractive index of a material is given as speed of light in vacuum divided by speed of light in the medium. So that is how you define the absolute refractive index of the material. Suppose you are given to find the refractive index of water, or if you say the refractive index of water is 1.33, this implies it is its absolute refractive index and it is the relative refractive index with respect to the vacuum. Then we have the relative refractive index, where you define the refractive index of one material with respect to another transparent material. As you can see here, relative refractive index of, say, one material, we call it M1, and another material, say we call it M2, can be defined in this manner. Refractive index of material M1 with respect to material M2. This was a case which we have dealt with in the previous class. So the refractive index, the relative refractive index of material 1 with respect to material 2 goes by this ratio. It is the velocity of the light in material 2 by the velocity of light in material 1. So if you are going to measure the relative refractive index of material 1 with respect to material 2, then you will have to do this ratio, where the velocity of light in material 2 comes on the numerator, and the velocity of the material you are going to measure, the refractive index of the material which you are going to measure should have its velocity in the denominator. Similarly, we can do the reciprocal of this, that is refractive index of material 2 with respect to material 1, and in its notation it looks like this: the refractive index of material 2 with respect to material 1 equals velocity of the material 1 over the velocity of the material 2. As you can see, these all can be related reciprocally, since it's V2 over V1 here and it's just V1 over V2 here, and it's clear that both of these are in fact reciprocals of one another. We know the left hand sides too must be reciprocals, which means N12 will be equal to 1 over N21. We have dealt that in our previous lecture. Now we have come across the two different kinds of refractive indexes. One was the absolute and the other one the relative refractive index. Now all these terminologies were defined based on velocities in the medium, based on velocities. So if the velocity of light is known in two different medias or two different materials, then we can do the ratio to find out their relative refractive indexes. But what if one material's refractive index alone is given and the refractive index of the second material is provided and nothing else is known? You can use those values to find out the relative refractive indexes between these two medias. So let me come to the point. The point is that we are going to define relative refractive index in terms of the absolute refractive indexes of the material. Suppose you have a material 1 and you have another material 2, and you go on to define the absolute refractive index of material 1. It's as simple as this: refractive index of material 1, which is n subscript 1, equals speed of light in vacuum, which is c, over the velocity in medium 1, which is v1. So c over v1, and we know the standard value of c is approximately equal to 3 into 10 raised to 8 meters per second. You know this notation is the scientific notation of 3 followed by 8 zeros. So the absolute refractive index of material 2 can be also found similarly, which is n subscript 2 is equal to c over v2. In a similar manner, we can go on ahead to define the refractive index of any material. Now we have n1, we have n2. What are these good for to define the relative refractive index? Now it's just as simple as this. We are going to see what a given ratio leads to. So if you are supposed to find the relative refractive index of material 1 with respect to material 2, let us see what these logical relations give us. Just do n1 over n2. Do n1 divided by n2. As you can see, I have done this over here. You have in the numerator n1 and you have n2 in the denominator, which equals, as per the definition of the absolute refractive indexes, the n1 stands for c over v1. See, it was over here. So I have replaced N1 with C over V1. And in the denominator, N2, which was C over V2, is just replaced right there. As you can see, in the numerator, we have a ratio which consists of a C in its numerator, and in the denominator we have another ratio again in which we have a C. Both of them cancel out, and what we are left over with is 1 over V1 divided by 1 over V2, which reciprocates to give us V2 over V1. These are all simple mathematical conundrums. What was V2 over V1? V2 over V1, as per our previous definition, was N12. So we have here N12 is nothing but the ratio of the refractive index N1 and N2, that is N12 equals N1 over N2. See, there is no further need to anymore describe the case where medium 2's refractive index is measured with relative to medium 1. It's as simple as the first case. Relative refractive index of material 2 with respect to material 1 is then, by doing the ratio N2 over N1, we get C over V2, similarly to the previous case, over C over V1, and we end up with V1 over V2, and we know V1 over V2 stands for N21. So N21 is found to be equal to N2 divided by N1. So that is how we can also calculate the relative refractive indexes of materials. Okay, so as far as the ideas we have studied, let us see how to apply them in a few situations. For example, I have brought to you here 3 examples, out of which the first example you can see here. If you can't read it, let me just read it out for you. The refractive index of water is 1.33. See, I have not attached any units since refractive index is just a ratio, so its value is a number. And as you can observe, the absolute refractive index of any material is always greater than 1. Absolute, let me repeat, just carefully listen, the relative refractive index of, the absolute refractive index of any material is exactly over 1, is greater than 1. Okay, let me continue. And that of olive oil is 1.47. See, olive oil is a transparent material which transmits light through it. Now the question is to calculate the relative refractive index. That's what I have abbreviated here. It stands for relative refractive index, RRI, of water with respect to olive oil, and that was the first part of the question, and second part is olive oils with respect to water. So you in this question you need to determine the relative refractive index of water with respect to olive oil and olive oil with respect to water. So it's just the same case, but reciprocals are to be found. So let me give you the solution to this. If you want, you can attempt it, or otherwise you can just look at it, how I illustrate the example. Let me write down the given factors. In the question, we are provided with the refractive index of water, which was the absolute refractive index of water, and I denote it by N subscript W, where W stands for water. So it is the refractive index of water is 1.33, and again we have the following information, that is about the refractive index of olive oil, and here N subscript O. So O stands for olive oil and NO represents the refractive index of olive oil, and which was 1.47. As you can see, out of these both, water seems to be rarer, olive oil seems to be optically denser, because as I have mentioned previously, the optical density is just the refractive index. So you can see optical density increases with refractive index value. So moving on to find the relative refractive indexes. Let me call water as the medium 1 and olive oil as the medium 2, or materials. Either way, it is good to go with M. So let me call water as medium 1 and olive oil as medium 2. Then relative refractive index of medium 1 with respect to medium 2 is given by N1 over N2. So here N1 comes first, so 1 on the numerator, and 2 comes second, that means N2 in the denominator. In a similar fashion, with our given abbreviations, given denoted terms, let me just show you how this works. So you want to find the relative refractive index of water with respect to olive oil. It's just the refractive index of water over refractive index of olive oil, and you just do the mathematics, 1.33 over 1.47, and it is calculated to be approximately equal to 0.904. So it's a value less than 1. That's relative refractive index. Relative refractive index can be either less than 1 or greater than 1, depending on the type of ratio you are taking. So let's move on to the second case. In the second case, we take olive oil as medium 1 and water as medium 2, and we find the relative refractive index of olive oil with respect to water. And what's that? NO, the refractive index of olive oil divided by refractive index of water. And what is the refractive index of olive oil? It was 1.47, and for the water case it was 1.33, and do the ratio and you find it is 1.105 approximately. See, here the relative refractive index is greater than 1. In the previous case it is less than 1. So it can vary. So that's how the solution is done. Now we have two more questions over here. Let me just adjust it properly so that you can see. Question 2 says, calculate the speed of light in water and glass if their refractive indexes are 1.33 and 1.5 respectively. I'll go on to third question later. Let me just do this first. So if you want, you can go ahead, attempt do this, or if you want me to do, just wait for 1, 2, 3. Okay. So going on with this second question solution, we write down the provided information. The given informations are the refractive index of water, which is 1.33, and refractive index of glass, which is 1.5. So according to the definition of the absolute refractive index of a material, the definition goes like this. The refractive index of the definition of Nm, that is refractive index of a material, is C, the speed of light in vacuum, divided by the speed of light in the material. So from this ratio you can see the information about the speed of light in the material is there, which we will isolate and form this equation, and this equation will give you the velocity, the value of the velocity of light in the medium. All you have to do is divide the velocity of light in vacuum by the refractive index of the material. Sorry, I have given here W, it's supposed to be Nm, but I think I just got confused with water already. So it's C over Nm. So you have to divide speed of light in vacuum by the value of the refractive index. So for water, speed of light is, see, I've just repeated the definition, and that's not required since we have already isolated the value for velocity. So velocity of water velocity of light in water, I'm sorry, I make a lot of mistakes while I say something because it's a live recording, so please just forgive me. Velocity of water, oh again I did that, I'm so sorry. Velocity of light or speed of light in water is c over the refractive index of the water itself, and that is 3 into 10 raised to 8 meter per second divided by 1.33, and the value of velocity of light in water is found to be 2.25 into 10 raised to 8 meter per second. Since this is a scientific notation, I am writing it in this manner. So it's less than the velocity of light in vacuum, obviously, because it is 3 lakhs and it is only 2.25 lakhs kilometers per second. Lakhs, I use lakhs when I say kilometers, and it is not for meter per second. Okay. So similarly for glass, the velocity of light in glass can be calculated using the similar equation. The velocity of light in glass is c over the refractive index of the glass, and it is 3 into 10 raised to 8 meter per second over 1.5, and it's an easy division over there. And as you can see, I have not stressed out or hidden any more answers for you. You can just directly see it's just 2 times 10 raised to 8 meter per second. So in glass it is even less fast, the light moves even less fast, or which is it moves more slowly in glass as compared to vacuum, and it is even slower in glass as compared to water. So you know now how to calculate the velocity of light in respective mediums. Over here I have made a chart, a table which shows a few patterns. I have given the material, we have vacuum. See, vacuum is actually not a material, but it is just a reference medium, and we have water, and we have glass, and I have arranged them in accordance to their increasing value of refractive index. So vacuum has a standard refractive index of 1, water has a refractive index of 1.33, and that of glass is 1.5. And on the third column I have indicated the speed of light in each material. In vacuum it is 3 into 10 raised to 8 meter per second. In water it is 2.25 into 10 raised to 8 meter per second, and in glass it is just 2 into 10 raised to 8 meter per second. As you can see, as the refractive index increases, the velocity or the speed of light in that particular medium starts getting lower and lower. So higher the refractive index means slower light moves through that medium. And as you can see from our previous equation, the velocity of the light in the medium was c over nw, which is velocity of the light in the medium was equal to the speed of light in vacuum over speed of light in the medium. Now from here you can redefine the refractive index. Refractive index can be redefined as you can see, you just do the cross multiplication. I'm sorry, not nw, it's n subscript n times v subscript m. So refractive index is another way defined as a factor that connects the velocity of light in the medium and the speed of light in vacuum. So it is the factor which says the speed of light in vacuum is this much times the speed of light in the medium. As you can see, let me repeat that, speed of light in vacuum is equal to refractive index times you multiply the refractive index, you multiply refractive index times the velocity of the light in the medium. So that is what the indicative of refractive index is. Refractive index indicates that the light moves several factors, a factor which is equal to the refractive index in the given medium. Now let me move on with the third question. The third question states, let me read out the third question. Predict the deviation of refracted ray. So the material, the ray in the second medium, I guess. So refracted ray with respect to, WRT stands for with respect to the normal when light moves from, so we have two cases. So you need to find deviation of the refracted ray when light moves from olive oil to water and water to glass. So no other informations are provided. But we have dealt with olive oil, water and glass in our previous cases. So we know their refractive index. So in this question, it is assumed that you already know the refractive indexes of olive oil, water and glass. I guess we may need to use them. So coming to the deviation of the path, or see when light enters from one medium to another medium, so this is the incident light. This ray is called the incident ray. It is incident at an oblique angle, in an oblique fashion. See, when a light is incident at an oblique fashion, implies there is a non-zero angle between the normal and the incident ray. So the incident ray is at a certain positive angle with respect to the normal. So at this angle, when the light crosses the interface, it suffers a deviation. It does not continue along its normal path, but instead it deviates either towards the normal or away from the normal. So this is the normal. So as you can see, if this was the path, this is towards the normal, it is moving towards the normal, and this is actually moving away from the normal. So whether it is moving away from the normal or whether it is moving towards the normal should be found out, and that is what indicates the deviation. So you all need to do is determine the angle of refraction in each cases. See, when the light ray moves from in two different materials, its deviation shows two things. One is it slows down in the second medium, or it moves faster in the second medium. So if it is moving, if the deviation is away from the normal, means the light ray is faster, and if it is lower, that means the deviation is towards the normal. So it will be moving towards the normal. So let me just analyze these two cases separately. So case 1. So case 1 states path of light deviates towards the normal. So that is the first case that we are going to look at, when the deviation is towards the normal. So in that case, the angle of refraction should be less than angle of incidence. Let me just go back to the previous figure. You can see if this angle has to be maintained, then the ray has to go straight in the normal manner. It has to go straight along, it has to continue along the same straight line. But no, that is not happening. So this angle changes. So the angle of refraction will not be equal to angle of incidence. It will be less here and will be larger here. So the case that we are studying, shows that the angle of refraction is less than the angle of incidence because the path deviates towards the normal. So in that case, the angle of refraction should be less than the angle of incidence. So when does this happen? Similarly, we have the case 2 where the path of the light deviates away from the normal. The path of the light deviates away from the normal, which means the angle of refraction is now more than the angle of incidence. So R should be greater than I. So both these cases, when do both these cases occur? Let me just take you to a deeper analysis. We have learned Snell's law in our previous lectures. Snell's law is the basic reason why all these happens. It is the relation between the angle of incidence and the angle of refraction. It's a trigonometric relation, and that is why you have sines involved. So what does Snell's law stated? In your syllabus based study, you are only supposed to learn that sine of the angle of incidence divided by sine of the angle of refraction is a constant. Doing this ratio gives you a constant for a given pair of medium. If you have medium water and if you have medium air, or you have olive oil here, so water and olive oil will always have this ratio equals a constant. So but that constant will change depending on if the mediums change. So suppose if you have glass over here and kerosene underneath, then this constant will change, but for that particular set this constant will remain same even if for any value of ice there will be a given value of R, provided for that particular medium this constant remains the same. So this is what Snell's law was. So how does this work on to solve our problem? For that, we will have to look at a more detailed version of the Snell's law itself. See, this version is not in your syllabus, but let me just show you how these things work. The Snell's law in its more detailed form looks like this. The refractive index of the medium in which the incident ray is times sine of the angle of incidence equals the refractive index of the refracting material times sine of the angle of refraction. So it reads like this: Ni sine I equals Nr sine R. So it's a very easy to read through. It's all you have to remember is Ni stands for the refractive index of the material in which the light comes from, and Nr is the refractive index of the material into which the light passes through or transmits into. So how does this equation help us? From the equation, if we manipulate it slightly changing the equation's form, writing sin I on the left hand side and bringing sin R to the left side, so you get is this following ratio: sin I over sin R, and bringing the Ni to the other side, to the right hand side, you get the following ratio: Nr by Ni. See, this is this form of Snell's law you have studied. The following ratio is supposed to be a constant. So now what you have found out is the value of the constant itself. The constant itself is actually the ratio of refractive indexes. So what was the what was Nr? Nr is the refractive index of the material, the second material. If you say the light transmitted to the second material's secondly, and Ni stands for the refractive index of the material of the first material where the light ray was incident. So this means NR and NR over NI means the relative refractive index of second material with respect to the first material. That is the constant, that is what the constant is. So that's a good thing that you know that. So let me just slide down little bit. So what you have found out is that NR over NI stands for the relative refractive index of R with respect to I mean material of R with respect to material of I, and that is what the constant that you have learned in the Snell's law was. The constant is nothing but the relative refractive index of the two mediums involved. So it means if the mediums change, that constant should also change. Okay, so let me slide down a little bit more. See, if the numerator term, which is NR, is greater than the denominator term, what happens in the following ratio? If in the right hand side, if the numerator is larger than the denominator, mathematically this must imply that the numerator in the left hand side, which is sin I, should be greater than the denominator sin R. And there is this peculiarity of sine functions, that if the ratio sine of the angle is greater than sine of some other angle, that means the angle themselves can be related in this manner, which means if sine of I is greater than sine of R, it only implies that I must be greater than R. So when does I greater than R thing happens? I greater than R happens when the light ray deviates towards the normal, which means light has slowed down. And if NR is less than NI, that is on the previous equation, if the numerator is less than the denominator, this would imply the numerator on the left hand side should also be less than the denominator. And as I have pointed to you, that sine functions have this peculiarity that if the ratios are connected via this relation, their angles must also be, which is nothing but if sin I is less than sin R, if sin I is less than sin R, it only implies that I must be less than R. So when does that occur? I less than R occurs means the refracted ray bends away from the normal. It bends away from the normal. So it only happens when medium 1 is optically denser than medium 2. So it's good to go with all this mathematical jargon. Those three problems were solved. Mathematically, we found out it was easy to solve them, no problem. But what is the physical? There are a lot of physical phenomena occurring behind it. There are, refractive index is good to go with as an indicator of the optical density. But what does it mean physically? Does it even have any physical significance? Because you are studying physics here, so you need to know the physics behind, whatever the physical phenomena that is occurring. The most interesting one is the following: visibility of transparent material. You have learned that transparent materials are those kind of materials which transmit light through them. If they transmit light through them, how the hell are you able to see transparent materials? If transparent materials allow light to pass through, then how are they visible to us? Basic visibility criteria is that at least it must cast a shadow, right or wrong? It must cast a shadow, at least it must cast a shadow, or at least it must reflect some light. If nothing is happening, then how the hell is it visible to us? So no material in the universe, I do not know, I mean the vacuum is actually the most transparent material, I guess, and even air is also highly transparent. That is why we are not able to see air. Air is a highly transparent material, just like vacuum is. But there are three basic reasons for other transparent materials to be visible. What are these reasons? Let me show you. Let me go through each one by one. Reason 1 is partial reflection. Reason 1 is partial reflection. So you might have seen no transparent material is actually perfectly transparent. You have seen materials, you go ahead, you go to a nearby car and you just look yourselves into the window, you comb your hair, you adjust your style, collars, everything, because you can see your goddamn face in it. Also, you do the same when you go near a stream. You can see if it is a settled down water body, then you could see your reflection in it. Even pure clean water has some reflection, shows some reflection of materials around it. Well, look at this building. It is made out of glass which are transparent, but you cannot see anything clearly. You are mostly seeing is reflection of the outdoor. You can see a tree over here. I don't know if it is a tree or anything, but you can see post lines all around. Still the inside lights are visible, the ceiling is visible. Even in that case, you are able to see the sky, there is cloud, it is all reflection. See, these kinds of partial reflections of the materials show us these transparent things are there or not. Moving on to the second basic reason. The second reason why transparent materials are visible is because of non-uniform refractive index. What the hell is that now? Or there is a difference in refractive index. Let me show you a video clip which really demonstrate this. Let me play this video. It's a video made by Veritasium, a very famous science channel in YouTube. As you can see in this video, the guy is lighting a matchstick and you can see hot air around it visible, and you can see dark patches of that hot air. Let me pause it here. Let me just pause it back here. See, in this you can see there are places where the hot gas is visible, and there are locations where it is dark and somewhere it is like folded. So somewhere it is less dark and somewhere it is too bright. So this actually happens because of differences in refractive index or non-uniform refractive index. See, refractive index in one region might be more than refractive index at the other region, because if refractive index is more, there will be more deviation, and hence the light from the other side will deviate so much that there will be no light coming in your direction, and there are other regions where there will be the refractive index is very in a medium manner, so the light coming from that part will be only partial. So this difference in or the non-uniformity in refractive index is the cause of the so-called visibility. So that is what non-uniform refractive index causes or helps you to clearly see even the transparent materials. If the refractive index is non-uniform, then the light bending at different points will be different, so the intensity of light reaching your eyes will also be different. So depending on the difference in the intensities of light, the invisible transparent medium starts to be visible. And the difference in refractive index, The difference in if the difference in refractive index is large, then there will be more visibility. Let me just demonstrate this too. So over here is a science and technology video where you see water on one side, one beaker, and there is this, I think there is this I guess it is it must be the sunflower oil on one side, and you can see two different rods, two glass rods being dipped into each material into each liquids. As it was clearly visible to you that you can see on the right side, you see the glass is still visible underneath, but on the left side where the liquid is a bit yellowish, you do not see the glass rod inside. It is invisible. See the visibility, the invisibility of the glass rod, that is the most funny part. That occurs because the the glass rod has a refractive index which is almost similar to the olive oil, not the olive oil but the sunflower oil inside the beaker on the left side. But whereas in the case of on the right side beaker, you can see the glass rod is still visible because the glass rod's refractive index is not nowhere close to the refractive index of the water. So that is the